Hello everybody and welcome to the Coopersmith Career Consulting Crash Course on Introduction to Life Processes. SCI102 is the course number. It's basically biology. We are going to be focusing on the life processes specifically. We're going to be discussing general life processes, and then we're going to be applying it to the life processes as they are applied in the human being. Other courses might deal with animals and plants and things like that. We're not really going to focus much on animals and plants except maybe a little bit tangentially, but we are going to be focusing mainly on the human being and the life processes. But before we even get to the human being, we'll have to discuss the background of what they are and what they do. There are various textbooks and resources, study guides that you are provided with, of course, but I'm not really going to be focusing on that in this video. I really intend this video to be kind of a standalone review that will give you the ability to be prepared for the final examination, generally speaking, by just reviewing whatever material there are in this course. This PowerPoint presentation over here that I'm going to use, you should have access to. If you don't, you should ask the appropriate person that's helping you with the course. And we are going to now begin with our discussion of life processes. Our first topic that we're going to cover is a little bit of basic chemistry. Of course, this is not really a chemistry course, but a little bit of basic chemistry is really necessary for biology. This unit, this section, is atoms, molecules, and life. Life is based on, well, everything is built from molecules, and molecules are built from atoms. A molecule essentially means the smallest thing in nature that cannot be broken down and still remain the same object. You can have one molecule of wood, you can have one molecule of water, you can have one molecule of iron, you can have one molecule of steel. If you break down the molecule any further, it's not going to be water or steel or whatever it is. You can break it down, but not retain its structure. The atom is the building blocks of molecules. Atoms in general, hopefully you might be familiar with it, but all the atoms that are in nature are based on elements. In other words, one atom means the smallest unit of a particular element. All of the elements are listed on the periodic table of the elements. You may have seen this before. This is unfortunately, I can't get the entire periodic table in the view over here, so I'm going to have to scroll around a little bit. But you can see it starts all the way at number 1, which is the H, which is hydrogen. Then it goes to helium, then lithium, beryllium, and I'm going to move back over here to the other side of the periodic table: boron, carbon, nitrogen, oxygen, fluorine, neon, etc., all the way into the low 100s when it comes to the elements. If this were a chemistry course, we would go through these in exhaustive detail, and we would discuss what the different properties of different atoms are and how they work, different elements are and how they work. We're not really going to do that because that's not really necessary, but I do want to show you a couple of things that are very important. Really, this number over here on top of each element is the number of protons that are in the element itself. There are 3 types of basic particles in an atom. There are the protons, neutrons, and electrons. The way an atom basically looks is that there is a material in the middle, those blue and red things in this particular diagram, and then there are the things swirling around the middle, and those are the black things in the diagram. The middle is called the nucleus, although in this diagram it looks like the nucleus takes up a large component of the atom, when in fact the nucleus is only a tiny, tiny, tiny little thing in the middle of the atom. But the nucleus, the middle things, the blue things and the red things, are the protons and the neutrons, and the things that fly in the outer circles, sometimes known as orbitals, are the electrons. Those are the black things. The protons are positively charged, the neutrons have no charge, and the electrons are negatively charged. In a typical atom, in its ground state, in other words, in its normal state, the number of protons is equal to the number of electrons, and therefore the atom is neutral. It has no charge overall. It has a certain number of positives and an equal number of negatives. If there are more electrons than there are protons in the atom for whatever reason, then the atom has a negative charge. If there are more electrons than protons, then it is negatively charged. If there are more protons than electrons, then it would be considered positively charged. Either way, as we'll discuss in a couple of minutes, that is what is called an ion. An ion is a charged particle. In the periodic table, this number above the name, above the letter that represents the element, H for hydrogen, Li for lithium, sodium, potassium, calcium, magnesium, all these other things over here. This number, this 1, this 3, this 4, this 11, 12, that represents the number of protons in the atom. So an atom with 1 proton is hydrogen. An atom with 3 protons is lithium. An atom with 11 protons is sodium. As we move to the other side of the periodic table over here, an atom with 8 protons is, of course, the very important element of oxygen. An atom with 17 protons, for example, is the element chlorine, etc. The important thing is that in its normal natural state, they would have the same number of electrons. For example, fluorine, which is F, which has 9 protons, would normally also have 9 electrons. If it doesn't, it would be considered an ion. Because ions are atoms with a charge. Atoms, the way this works in terms of charges, is that the number of protons stays the same. Remember, the idea in ion is when you have a different number of protons as electrons. Theoretically, there would be 2 ways to do that. Either you could add or take away protons, or add or take away electrons. Problem is, you can't do that with the protons. If you change the number of protons, it wouldn't be that element anymore. If you had, for example, an atom of potassium, which is K, which is 19 protons, and you changed the number of protons, it wouldn't be potassium anymore. If you added a proton, for example, you'd have calcium. If you added 3 protons, you'd have Ti, whatever that stands for. If you took away a proton, well, then you'd have Ar, which is the 18, and you'd have argon. So you do not take in, while that's theoretically possible in certain ways, you don't usually create an ion by changing the number of protons. Instead, you change the number of electrons. So for example, if you have sodium, which is 11, and you have 11 electrons, which is a neutrally charged sodium atom, if you add an electron, well, now it is negatively charged. If you subtract an electron, well, now it is positively charged. Now you'd only have 10 electrons, and you'd have an overall charge of +1. Take hydrogen, for example, which has 1 proton and 1 electron. If you take away the electron, well, hydrogen is now +1 charge, because it's got 1 proton and 0 electrons. If you added an electron, well, now you'd have a charge of -1, because you'd have 1 proton and 2 electrons. The next thing that's important to know about about elements and molecules, is that elements do not tend to stay only with each other. Atoms tend to bond with other atoms of different elements. If you, for example, never had any bonds between different atoms, then the only substances that would exist would be the ones on the periodic table, things like hydrogen and chlorine and oxygen and things like that. But of course, we know that there are much more complex substances like quartz and water and sugar and all the things that we use and that we interact with on a day-to-day basis are actually many different atoms that are combined with each other. And they are combined through what are called chemical bonds. A chemical bond is, simply enough, a bond that combines 2 atoms together. There are 2 basic types of bonds. The differences between them are very subtle. We'll very, very quickly go over them. An ionic bond is essentially when you've got 2 atoms that are next to each other, and one of them kind of borrows the other atom's electron. Let's say, for example, you've got sodium and chlorine. Sodium is Na on the periodic table, and chlorine is Cl on the periodic table. We look over here, we've got sodium, which has 11 protons, And we've got Cl, which is chlorine. By the way, sodium and chlorine, NaCl, is actually sodium chloride, otherwise known as regular plain old table salt. When you pass the salt and put it on your bread or soup or whatever it is, that is sodium chloride. Now, what happens when you have a bond between sodium and chlorine, for reasons that I don't want to get into that you might know from your high school chemistry class or whatever it is, if you've taken it, or even elementary school chemistry class, sodium tends to lose an electron. Long story short, the reason is because the way the electrons are structured and the orbitals that they're on, it's more natural for there to be 10 electrons in an atom than for 11. A 10 fills an orbital, and the 11th is just kind of hanging out there all by itself. So sodium has a very strong tendency to lose an electron, and therefore become a positively charged. If sodium loses an electron, now it's only got 10 electrons and 11 protons, it becomes positively charged. Chlorine, on the other hand, has a very strong tendency the opposite. The number that fills up the orbital in the chlorine is 18. 18 is a much more comfortable number, so to speak, to have than 17. So chlorine, on the other hand, tends to gain an electron. And when chlorine gains an electron, it's got 17 protons and 18 electrons, and that makes it a negative one charge. Because of that tendency, sodium tending to gain an electron and chlorine tending to lose an electron, those two tend to come together in very strong bonds. So just to put it in other terms, the sodium is very happy to give up an electron, and the chlorine is very happy to take an electron. And that kind of bond is called an ionic bond, because they're both ions. The sodium becomes a positive ion, and the chlorine becomes a negative ion. Looking at this diagram, the one on the left over here is a normal natural state sodium ion, which has 11 electrons. The protons and the neutrons are in the middle over here in the nucleus, and then the electrons would be on the outer rings. And you got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And notice the 11th one is all the way out here, all by itself on its own ring. That is not a particularly comfortable state for an atom, and therefore it can lose an ion. It can lose an electron, and go down to only two orbitals that have 10 electrons altogether. The chlorine, on the other hand, in a sodium chloride ionic bond, it starts off as the opposite. It starts off, remember, with 17 electrons. Here's the nucleus in the middle. It's got 17 electrons floating around the outside. And notice this outer wall of electrons, this outer orbital of electrons, is missing one. You got 2 over here, 2 over here, 2 over here, and 1 over here. That state is the reason why a chlorine atom will have a strong tendency to gain an electron. When you have this combination, the sodium atom, which is only too happy to give up an electron, combines with the chlorine atom, which is only too happy to get an electron, and what you have is the result over here. You have the sodium combining with the chlorine, so that the sodium is a positive ion and the chlorine is a negative ion, and the two things come together in an ionic bond, which is NaCl, also otherwise known as sodium chloride, otherwise known as table salt. The other type of chemical bond that exists, other than the ionic bond, is called the covalent bond. The covalent bond is similar to the ionic bond, except that instead of one atom giving up an electron and the other atom gaining it, the covalent bond is where the two atoms kind of share that last electron. Here's an example of a covalent bond. This example of a bonded molecule actually happens to be methane, which is CH4, 1 carbon and 4 hydrogens. This is an example of a covalent bond because the red circles are electrons from the hydrogen. Remember, hydrogen was a 1 on the periodic table and only had 1 proton and therefore 1 electron. Carbon happens to be a 6 on the periodic table, but the way carbon and hydrogen combine, and the way many other types of substances combine, is rather than the hydrogen giving up an electron and the carbon getting it, they kind of share electrons. One carbon electron shares, or comes together, with one hydrogen electron. So that's an example of methane. Here's another example. The next, really a big example, one of the most important examples we know of, and that is water. Water is H2O, which means 2 hydrogens and 1 oxygen. And they come together through this process of sharing the electrons. And hydrogen bonding also, hydrogen bonds are really kind of a subset of covalent bonds, but hydrogen bonds are attraction between hydrogen and another substance, such as nitrogen or oxygen. Water molecules, as we just discussed, is a very important type of chemical compound. It's made up of hydrogen and oxygen, 2 hydrogens and 1 oxygen. That's why, as you probably know already, hopefully know already, water is sometimes known as H2O, 2 hydrogens and 1 oxygen. This is the diagram that we just looked at. This is one water molecule on the upper left-hand side. Notice the oxygen is bigger because the oxygen has a number of protons of 8, whereas the hydrogens only have 1. This diagram is not really to scale. The oxygen is really much bigger than the hydrogen atoms. In this one, it looks like the hydrogens are just a little smaller. They're actually much smaller. But water is a substance whereby the hydrogens are bonded to each other. And that's why sometimes you'll hear water being referred to as being hydrogen bonds. And the reason is because the hydrogens of the different water molecules are bonded to each other. And because of that, water has many very important and very unusual properties. We're going to discuss some of these. And some of these are necessary for human life to exist. So we're obviously very happy that water does have some of these particular types of molecules. First of all, water has, like many other substances, cohesion, which means the tendency for molecules of a single type to stick together. Water especially has this element of cohesion, more so than, let's say, for example, sand. If you dropped a bunch of sand molecules, or not molecules, but grains, let's say grains of sand, they would scatter out all over the place. They would not bond to each other at all. Water, on the other hand, does. If you've ever filled up a cup a little bit higher than the cup would ordinarily hold, and you see there's kind of like a very small, low bubble in the middle. It's hard for me to describe it. Let me look for a picture. Okay, there we go. Found one. I'm sure you've all experienced this. This is a glass that you filled with water, and even though the water is actually a little bit higher than the glass, and you would think that it would just kind of spill out the side, very often the water kind of holds together and does not spill over the side. That phenomenon is known as surface tension, and the reason for it is the natural sticking together that water molecules do. All the water molecules stick together. Once you puncture it, like if you stick your hand in the top, then you might see the whole thing kind of spill out over the side because you broke the surface tension. That's also why droplets of water attached to something, like this example of some droplets of water on a leaf, which you've seen obviously an infinite number of times in various contexts, droplets of water stick together really for the same reason, based on this cohesion, this concept that water molecules stick together based on their hydrogen bonds. And this process also causes what's sometimes known as capillary action, which is very important for plants and leaves. We're not going to discuss it in too much detail, but basically the way it works is that water, when it goes into a root or goes into some kind of a filament, some kind of a hair on, it doesn't have to be a plant, it could be, pretty much anything, the water actually gets drawn naturally with the other water that, it kind of gets drawn up the plant. Like, for example, the plant water enters the roots and gets drawn up the bark of a tree all the way to the leaves where they're needed. So in order for the water to reach the leaves, water fills tiny tubes that connect the root, stem, and leaves. Before water can evaporate, it gets pulled up naturally to all the way to the leaf surface. And that allows it to be pulled upward in a chain, which is a very unusual property. I have just, again, let me give you one quick example over here. I wanted to show you a little experiment that somebody did. I just want to show you how this works so you get a little bit of a view that just let me, well, 1 second. I'm sorry, I needed to find you a better experiment than that. The other one you couldn't really see very well. So this is just an example of capillary action that I thought was very interesting. The person puts the red water, a paper towel, really just a folded up regular paper towel that you can do in red water on the right, and a blank cup or an empty cup on the left. And look what happens. You've probably noticed this when you use a regular Bounty or some kind of paper towel, and you put it, and you put it on the floor, and it soaks it up. Even if you don't actually scrape it, you just kind of put it in the whole paper towel kind of draws the water. And the reason why it's drawing the water like that is because of capillary action. And of course, you can see over here, this is a time lapse. Doesn't happen really this quickly, but the water kind of gets drawn from one to the other until the two cups will actually level out. And so that's an example of cohesion and how that works. Surface tension we also discussed is really the same concept, the tendency for water to resist being broken, and therefore it is produced by this concept of cohesion that we discussed in the last few minutes. Another very important characteristic of water is the water temperature itself and how it behaves with its environment. First of all, water has among the highest specific heat capacities of any substance, which means water is very difficult to heat up and it's very difficult to cool down. I wouldn't say difficult, but it takes a long time and it takes a lot of energy. It's a lot easier, for example, to heat up metal quickly than it is to heat up water. If you take a pot or a pan and it's empty and you put it under a fire, it's going to heat up extremely quickly, whereas if it's full of water, it's going to heat up much more slowly. And the opposite is true. It's also going to cool off much more slowly than if it were empty, or if it were filled with metal or some other object that's not water. The specific heat of an object literally means the amount of energy it takes 1 gram to heat 1 gram by 1 degree Celsius. The specific heat of water is 1, which means it takes 1 calorie of energy to heat 1 gram of water by 1 degree Celsius. Whereas metal and other objects have much lower specific heats. Most metals, for example, have specific heats that are somewhere between 1/25th of that of water and maybe about 1/5. Aluminum is about 1/5 of water. Lead is about 1/25th of water. The point is the heat capacity, the ability to absorb heat is much, much lower when it comes to metal and pretty much every other substance on Earth than when it comes to water. That's why, by the way, in case you're curious, islands or places that get their weather from the ocean, like the west coast of the United States, where the weather blows in from the Pacific Ocean, tend to be much more moderate than places in the middle of the continent or places that are surrounded by huge swaths of land, like Siberia, where the temperatures get very high or very low, depending on whether it's summer or winter. This example is a pretty simple example. If you, as we discussed before, you put a pot of water on the fire, the pot is going to get hot very quickly. The water, on the other hand, is going to take much, much longer to warm up. The amount of water it takes to turn, there are really 3 states of water, just like every other object. There's the solid state of water, which is ice. There is the liquid state of water, which is water. And then there is the gas state of water, which is steam, or water vapor. The amount of heat needed to make a substance evaporate is called its heat of vaporization, and water has a very, very high heat of vaporization. It's about 540 calories per every gram. That means to vaporize 1 gram of water, you need 540 calories of heat, which is, a substantial amount of heat. And this is one of the reasons why when you sweat, or even when you splash water on your face, it cools you off. Normally, if you go outside and it's 95 degrees and you're running around a lot and you get very hot, if you wouldn't sweat, your skin would get extremely hot very quickly. The way sweat works, or the way water that you splash on your face works, is the hottest molecules, the molecules that are moving the quickest, which means the hottest molecules, they evaporate. They basically heat up the water that's on your face or that's on your arms, and they go ahead and evaporate. And what's left over is just the cooler molecules. The hottest molecules turned into steam and evaporated into the air, and the rest of them stayed on you. That's why and you can try this, if you're very hot and you splash warm water on your face, it's still going to cool you off. Maybe not in the first millisecond, but after a few seconds it's going to cool you off. And the reason is because you splashed even warm water on your face, but the hot molecules on your skin and the hot molecules that are floating around evaporated into the air, whereas the cold molecules, or the cooler molecules, so to speak, are the ones that are left on your face, and that's going to cool you. So, I mean, don't do this with scalding water, obviously, then you're going to hurt yourself. But you take warm water, 100, 105, 110 degree water, as long as it's not scalding and it's not going to hurt you, you try splashing that in your face, it's still going to cool you off after a few seconds, because the hottest molecules are going to evaporate and the cooler molecules are going to stay there. Other interactions with molecules, there are a few other things that are important. First of all, water is what's sometimes referred to as a universal solvent. Water is one of the best ways to break down molecules. Some things break down more easily than others. Substances that break down are called substances that break other things down, that allow other things to be broken apart, are called solvents. Water is an excellent solvent. For example, when you put salt in water, it's no longer the same molecular salt. Instead, you get, well, as we all know, you get salt water. Sugar also. Now, sugar doesn't dissolve quite as well as salt does, but it also dissolves in water. You take your morning coffee, even if it's cool, even if it's iced coffee, you put it in a packet of sugar, you stir it around. Maybe not every grain of sugar is going to dissolve. Some of them are going to stay in the bottom, but a lot of them, or most of them, depending on how well you stir, are going to dissolve, because water is a tremendous solvent. Water breaks things down. That's one of the reasons why water is so good at cleaning. You put it over a surface, and whatever dirt or dust or dirty stuff is on the counter can be dissolved and washed away by the water. Other substances, other things that are other liquids that are not water, that don't have water in them, would obviously not have the same degree of ability to dissolve things, and therefore wouldn't be as good a cleaning agent. A solution means a liquid that has something dissolved in it. Salt water, for example, is a solution. We may not think of it as a solution. Solution we think of sometimes as being, funny chemical properties. But salt water is a solution because it's water that has broken down atoms and broken down molecules in them. Broken down salt molecules. Instead of the sodium chloride being there, now it's a bunch of sodium ions floating around and a bunch of chlorine ions floating around, and obviously it tastes a lot different than it would be just plain old regular water. And this is kind of a review. Salt is made of sodium and chlorine. They're held together by an ionic bond. The positive sodium ion and the negative chlorine ion. When the salt's dropped into the water, the sodium is attracted to the negative oxygen molecules that are floating around, and the chlorine to the positive ones, and this is eventually how the salt ends up dissolving. Not every type of molecule actually dissolves in water. Water dissolves polar molecules. In other words, molecules that have charges at different ends. Basically, ionically bonded molecules tend to dissolve more than molecules that have covalent bonds. Because if you remember when we discussed bonding, ionic bonding, and just for review, if you remember, this was an example of an ionic bond where you had one atom gave away its electron to the other one. Well, now if you think about these two things being bonded together, on this side you've got positive territory because you have an electron lost, and on this side you've got negative territory. Now if you think about putting this in water, well, the positive oxygen molecules will interact with this area, which is negative, and the negative oxygen molecules will interact with this area, which is positive, and that will end up being dissolved very well in water. Substances that are not as polar, like the methane we saw before, things that don't have strong ionic bonds, those are less likely to be dissolved in water. So water doesn't dissolve molecules with nonpolar covalent bonds because they don't have poles with a charge. They don't have sides, they don't have ends that would naturally be attracted to the positive or negative oxygen molecules. So for example, fats and oils are hydrophobic, which means that they do not dissolve in water. Water has an effect on these things. If you've ever put a piece of fat or something, or cheese or whatever it is in water, you know that it has an effect and mixes it around a little bit, but it doesn't dissolve to the same way that something like salt would. And finally, for this chapter, I want to just really do some vocabulary words that are going to be important later on in the course when it comes to the chemistry involved in living things. Synthesis means the building of two substances by combining them. You have two smaller substances, put them together in one big substance, now you've got synthesis. You take two monosaccharides, which means two single sugar molecules, and combine them into a disaccharide, which is a double sugar molecule. Common sense. When you do so by taking out a water, when you build two things by basically removing a water molecule from them and that combines them, that's called dehydration synthesis. In a chemistry course, we'd spend a lot more time on that. This just an example: sodium chloride is formed by dehydration synthesis. This formation of table salt, I just made this slide. The reason why it's called dehydration synthesis is the way table salt is actually formed. You don't actually take the sodium and chlorine and put them together directly. What you need is, first you need NaOH, which is a sodium, an oxygen, and a hydrogen. That's called sodium hydroxide, plus HCl, that should be small l, which is a hydrogen and a chlorine, also known as hydrochloric acid. And what you get is an H2O, which is a water, plus a sodium chloride, which is a table salt molecule. That's how table salt is actually formed in a reaction. And it's called dehydration synthesis because what you're doing is you're making the sodium chloride by taking out a water, by producing a water. So it's called dehydration synthesis. The opposite is called if you look at the slide over here, a hydrogen ion is removed, and a hydroxyl, which is an O and an H, is combined into a water, and whatever's left over. So, if you look at this formula, what's forming the water? Well, this OH, which is called a hydroxyl, an OH, and this hydrogen ion, this H, and they're combined to form the water, and what's left over is this Na, that's sodium, and this Cl, that chlorine, and they eventually combine. That's why it's called dehydration synthesis. Hydrolysis is the opposite. If you imagine this is being reversed, you have the NaCl plus the I can write this just as easily down here. H2O plus the NaCl, and you add those two together to get sodium hydroxide and hydrogen and hydrochloric acid. You can just say reverse. Okay, well, I should probably spell that correctly. Make it a little bit bigger to make it a little bit more visible. There we go. Okay, so this is dehydration synthesis. You're producing a water. In other words, taking a water out of this stuff in order to produce sodium chloride. And the reverse is called hydrolysis. Basically, you're taking NaCl, adding a water, so that's why hydro, adding a water, and you're getting sodium hydroxide and hydrochloric acid. Just the exact opposite. One of the things we do when we digest simple sugars and various other types of molecules, we use hydrolysis to break it down so that our individual cells can use it. Here's just another example, very quick, basic example for hydrolysis or dehydration synthesis. This doesn't even really mean that much. All it is just an idea of sometimes you add water in order to break it down, or you can subtract water, draw out a water, produce a water, in order to link up two compounds to make one final product. So just a little review for the end of this chapter. Let's look at these two multiple choice questions, sample multiple choice questions. And we've got sweating is a useful cooling mechanism because water A takes up a great deal of heat in changing from solid to liquid. Can exist in two states at temperatures common on Earth, is an outstanding solvent, takes up a great deal of heat changing from liquid to gas, or ionizes readily. Well, many of these statements are true statements, but only one of them actually help. Remember, when you sweat, what happens is the hot molecules become vapor and move into the environment, while the rest kind of stay on your skin, and those are the cool ones. A, which is from solid to liquid, that's the melting. That's melting from ice to water. That has nothing to do with sweating. There's no ice involved in sweating. Can exist in two states at temperature common on the Earth. That's true. I mean, it happens to be true that there is solid water and liquid water at various places on the Earth, but that has nothing to do with sweating again. Is an outstanding solvent. Another true statement, but again, has nothing to do with sweating. What about D? Takes up a great deal of heat to change from liquid to gas, to evaporate. Yeah. Takes up a lot of the heat on your skin goes to vaporizing some of the molecules into the air, and the rest are the cool ones. And it ionizes readily, which isn't even a true statement. Doesn't even make sense in the context of this question. So the only answer that really makes any sense is D. Number 2, you drop a handful of salt into a glass of water, which best describes what's happening. Okay, A, the positively charged hydrogen ends of the water molecule are attached to the chloride ions. Well, remember, chlorine tends to be a negative ion, because chlorine tends to gain an electron, and so therefore it would be attracted to something that is positively charged. So that makes sense. B, the positively charged hydrogen ends of the water are attracted to sodium ions. Now sodiums tend to be positively charged, so positive and positive would not attract to each other. So sodium and chlorine ions form a covalent bond. It's not true. They form an ionic bond. In any case, it has nothing to do with dissolving. And water and sodium form a covalent bond. That doesn't make any sense anyway. So the only answer that makes any sense over here would be A. A and B are both look like good choices, but you remember that sodium tends to turn into a positive ion, and chlorine tends to turn into a negative ion. So chlorine would be attracted to something positively charged, whereas sodium would be attracted to something negatively charged.